Okay, this will be the maybe the last video of chapter 10. So in this video, I'm going to show you some like 3 numerical examples of one-tailed test. Okay, so first numerical example is what we considered in the previous video. So suppose that Starbucks Grande iced coffee is supposed to have 16 ounces, but someone claimed that it is too small. It seems too small, so I need to check it. So our null hypothesis is 16 ounces, but if it turns out to be smaller than 16 ounces, I'm going to reject my null hypothesis. Okay? So, like if it's greater than 16 ounces, I don't care, or that's not likely, or that's not possible. Starbucks won't do it on purpose. So if it was greater than 16, then literally that would be a mistake by Starbucks, but that's not something to punish, right? That will be rather a random error. So I only care about whether it is too small. Okay, that's our hypothesis to test. So and in under this setup, we have a sample of 100 observations, and we found that the sample average, the average of 100 grande coffees was a little short of 16 ounces, so 15.6 ounces, and their standard deviation is 3, right? So this like 0.4 ounce lower than what it's supposed to be could be simple random error, like measurement error, or could be a serious problem, like cheating, right? So we are going to calculate t-statistic and p-value and critical value under this setup, okay? First, the t-statistic, remember the t-statistic is the difference between the sample average from the data and the true mean I assumed in the hypothesis, the mean that I believe to be true in the hypothesis. So 15.6 minus 16, so data and your hypothesis, standardized by the standard error, standard deviation divided by the square root of sample size. And then you will get 1.33333, keep going, but simply let's say 1.33, that is the t-statistic. So as you see, there is no difference. The t-statistic itself is neutral, and it's not affected by the hypothesis, like alternative hypothesis. So t-statistic does not depend on the alternative hypothesis, so it does not change when you think about one-tailed test. So it's simple. Now I am going to calculate the p-value based on the t-statistic. Remember, we are going to reject on the lower tail only, right? So the p-value is calculated only on the lower tail like this. And so probability of standard normal distribution is smaller than our p-value, our t-statistic. That is 9.18%. Okay, so if you use this p-value, based on this p-value, the decision rule is to compare with the significance level, right? P-value is already calculated, so if the significance level is greater than the p-value, you are going to reject the null hypothesis, right? So you are willing to reject 10% of outcomes, but your outcome is top 9% suspicious. So it's one of the most top 10% suspicious outcomes. So you are going to reject when p-value is smaller than alpha. But if alpha was smaller than the p-value, you don't reject the null hypothesis. Okay, so in the p-value approach, we are going to make these decisions depending on your significance level. Okay. If you directly make decision based on the t-statistic, then remember we are going to reject only when t is too small, too much negative. So the cutoff is minus z alpha, not alpha over 2. In our case, t was 1.33, and depending on the significance levels, our cutoffs are these values, right? So that is, if you choose 10%, the cutoff is 1.28. So if you take minus sign here, 1.33 is smaller than minus 1.28. So you have to reject the null hypothesis. But if you choose 5% or 1%, your margin is larger, so the margin covers minus 1.33. So your t statistic is the standardized difference is within the margin you allow for the random error, right? So in these two cases, you do not reject the null hypothesis. So that means like the t-statistic approach is consistent with the p-value approach, rejected only at 10%, but not rejected at 1 or 5%. Okay, and remember, those numbers are from the new set of numbers different from the confidence interval or two-tailed test. Okay, so have to be careful with that. Finally, the critical value approach. We are going to choose only one critical value below the null hypothesis because we are rejecting from below. So like mu 0 is your null hypothesis, which is 16 ounces, minus, because it's below, z alpha is the number we just used, and standard error is given, 3 divided by square root of 100. So in our case, x bar is given, mu 0 is given, like 16, and z alpha is given by those numbers, and then all these numbers are given, right? So compare them. The sample average is 15.6. If it's smaller than your cutoff, your threshold, then you are going to reject the null hypothesis. So depending on the significance level, if your significance level is 10%, that means you are willing to reject more. You are willing to punish more strictly, right? So if the sample average is below 15.616, then you are going to punish Starbucks. Okay, so in this case, yes, you are going to punish your sample average is below your threshold, so you will be punishing Starbucks. Okay. But if alpha is 5% or 1%, that means you are more generous. So your margin is much lower, much larger. So your threshold is much lower. So 15.6 ounces is sufficiently large given your thresholds at 5 or 1%. So you do not reject the null hypothesis in these cases. Okay. So this is how we carry out hypothesis testing with inequality, especially when we reject if the outcome is too small. Okay. Now I'm going to change the direction of the inequality. Like for example, I ordered a grande coffee. Now grande iced coffee. Now I think it's too hot, it's too lukewarm, not cold enough. Suppose that it's not true, but according to the manual, suppose that iced coffees are supposed to be at a temperature 40 degrees or lower. Should be cold enough, right? Like it's an iced coffee. So I am going to punish. I don't know if it's a reasonable reason to punish the coffee shop. Anyhow, suppose that I believe that the temperature is 40 degrees, as in the manual, at most 40 degrees. But if it's greater than 40 degrees, then the quality of the coffee shop is not good. I will decide I'm not going to come back this coffee shop again. So it's a punishment. So, and in this scenario, I ordered 100 iced coffees, and I found that their average temperature is slightly above 40 degrees. Oh, too warm, not enough, not cold enough. And their standard deviation is 4. So you are going to do the hypothesis testing. So try to calculate the p-value. And remember, you are going to calculate t-statistic, and then you are going to calculate p-value using normal distribution calculator. What you need to remember is I am interested only in the upper tail, right? If it's cold enough, like the temperature is low enough, not a problem. But if it's too high, then I'm going to reject, and I will not come back to this coffee shop. So calculate the p-value based on that one-tail test. Okay, so let me turn the page. So first, the t-statistic does not change. It's the same t-statistic as we did earlier. So you believe that in your hypothesis, the temperature would be 40 degrees, but actually it turns out to be 40.7, right? In the sample of 100 coffees. And standardize the difference by standard deviation 4 divided by sample size 100. So the standardized difference is 1.75. That is the same t-statistic regardless of alternative hypothesis. But we are, as I said, we are going to reject only on the upper tail. The p-value only includes the upper tail probability, right? Like this. We calculate probability greater than, even higher than 1.75, which is 4.006%. Okay, so this is your p-value, which means this difference is top 4% suspicious, right? It's a little bit too high, right? And then you are going to reject. You may reject, or not. I did not give you the significance level yet, but you have to compare this with your significance level. So now I give you the significance level 5%, and then in this case, you calculate the critical value. Pause the video and calculate the critical value. Because we are rejecting on the upper tail, your critical value must be at least greater than 40 degrees. Because if the average temperature is too high, then you are going to reject. So it must be greater than 40 degrees. So A and B cannot be the answer. And significance level is 5%. And remember, we are going to use 5% only on one tail. So you have to find the constant accordingly. Okay, I will turn the page. So you have to use Z alpha, not alpha over 2. That is, you are going to use 1.64. 1.64 is the new constant from standard normal distribution. And mu0 is 40 degrees in your hypothesis. And standard deviation is 4, square root sample size. Sample size is 100, so denominator must be 10. And then you get this number. So if the temperature is greater than 40.656 degrees, then you believe, oh, this coffee shop's iced coffees are too warm, so you are not coming back. You're going to punish the coffee shop by not going back. Okay. Yeah. So in the end, you are going to reject the null hypothesis because the sample average compared with the critical value is too high, right? The sample average is too high, higher than your acceptance region. You cannot accept anything higher than 40.656 degrees, and it is higher. So, it's rejected. And now I will think about type 1 and type 2 error probabilities from one-tail test case, right? Everything is one tail, okay? So first, type 1 error probability. I said type 1 error probability is always the significance level. Still, no matter it's one tail or two tail. So if you wanted to see that from algebra, you can just follow the same logic. So we are going to make a type 1 error when you reject a true null hypothesis. So when you rejection means x bar is greater than the critical value, right? X bar is greater than the critical value under the condition that the null hypothesis is true, which means the true mean is 40 degrees. And if you do calculation, do the algebra, standardization, right? Standardize x bar and the other side, then you are going to do this. And you go back to 1.64, which is exactly this guy. So mean and the standard error, like that you used for the critical value, are the same mean and critical values you use for the standardization. So basically, they are, it's kind of reverse transformation. So in the end, you are going back to alpha by construction. So the type 1 error probability does not need any algebra. It's always the significance level. Okay. And one more thing. So even though I gave you the sample average 40.7, but you should not use it when you calculate type 1 error, right? Already you rejected the null hypothesis, but it doesn't mean it is 100%. So we are now treating x bar, the sample average, as a random variable, as an unrealized random variable. So you do not use the specific number for x bar. Now we are to calculate type 2 error probability, which is a little more complicated. Now I'll assume that the true mean is 41 degrees, which is 1 degree above the manual. So the manual is not followed correctly. And then type 2 error probability. Type 2 error happens when you don't reject the wrong hypothesis. So because the true mean is 41, your null hypothesis is wrong. Your hypothesis is wrong. So if you don't reject it, that is type 2 error. So you don't reject the null hypothesis if sample average is smaller than the critical value. Okay? So you need standardization again. But in this standardization, you are going to use the true mean that you assumed, different from the null hypothesis, right? Standard deviation and the sample size are the same as before. So you will get minus 0.86 after standardization. That is 19.489%. So this is the type 2 error probability. So if the iced coffee's temperature is 1 degree higher than the manual, you will not tell that with nearly 19%. Right? You are not going to tell if it's cold enough or not with this probability. In other words, the power is 80%, which means with 80%, 80.511%, you will exactly tell the coffee is too hot, right? Too warm, right? So you will be successfully detect the wrong temperature with 80.511%, right? That's how we like. So basic idea is the same as what we did in the earlier chapters, earlier slides. So the final numerical example, I'm going to consider Affordable Care Act as an example, but it's nothing, of course, nothing political or I don't, just as an example to be more realistic. So before the Affordable Care Act, like which took place in 2013, um, like this is the health insurance coverage distribution. Some people, like say, like 48% covered by the employer, but 13.6% were not insured, did not have any insurance. But after the Affordable Care Act took place, the portion of the uninsured people decreased to 9.9%, right? So according to healthinsurance.org. So I am just motivated by this example, and I will make the problem like numbers more simpler. We will assume that 80% of people had health insurance before the policy change, right? But after the change, I don't know, like say now we are living in, like it's 10 years ago. When you implement a policy, the data are not clearly shown up. So we have to do some statistical inference about the proportion of those who have health insurance after the policy change. After the policy change. Before it is known to be 80%, but after it's unknown. So I'd like to test if this unknown P, the coverage after the change is higher than 80% or not, right? And here, on underlying assumption as an economist, I believe that it won't fall. Like the policy change does not cause P, the coverage probability to decrease. I guess it's the same or greater, right? Even if it's lower than 80%, I guess that it's for something else, right? That's just economics, like economists' intuition, right? The policy will not have any negative impact on the coverage, but if it has no impact, that already means it's not effective. Okay, in this case, usually the hypotheses are set up this way because I'm going to like especially if you want to show that the policy has critical impact, sufficient effect on the coverage probability, then you want to reject the null hypothesis of no effectiveness. That means there is a strong evidence supporting this policy change. So anyhow, my null hypothesis is that the policy change has no impact. Versus the alternative hypothesis is greater, like the policy change increased the insurance coverage rate. So it is an upper tail test, right? I don't worry about the probability decreases after the change, right? That is not likely by the economic intuition. But if it's up or the same, that's what we are going to do. In this case, we have to put equality as the null hypothesis, right? Okay, given this setup, I guess you are familiar with this trick. So this is a binary variable again. So we have to use the standard deviation this way. And suppose that you observe in the data of 100 observations, you found that 86 people had some kind of health insurance, right? Okay, that is data. And this is the binary distribution formula. Now then, remember, according to the standard deviation formula, we have to calculate standard deviation this way, but the point is, what kind of parameter do we need to use to calculate the, say, t-statistic? The answer is, in the t-statistic, we still assume that the null hypothesis is true. if our null hypothesis is true, then this is the standardized difference. Okay, so we are going to calculate the standard deviation using our null hypothesis, 80%. So if the probability was 80%, the standard deviation must be 0.4. So use this to calculate the t statistic. Okay, when you calculate the t statistic, still it's a step, the first step to make the decision, and in this case, the null hypothesis is assumed true. Okay, then t statistic is calculated this way. Data is 86%, your belief is 80%, and standardized this way, which is 1.5%. And then determine, just based on the t-stat, or you may calculate p-value, check if the null hypothesis is rejected or not at 5% significance level. Remember, it is one-tail test, upper tail test. So you reject the null hypothesis if your observation is sufficiently higher than 80% at 5%, like significance level 5%. Okay, pause the video now. You will need some algebra and do some calculation. Let's see. So if you take the t-statistic approach, the cutoff is Z alpha. Z alpha for 5% significance level is 1.64. So compared with 1.64, your t-statistic is too small. Small enough, not large enough to reject the null hypothesis. So you cannot reject. If you take the p-value approach, you are going to calculate the probability on the upper tail because you reject on the upper tail. So you are going to calculate probability greater than the t-statistic 1.5. That is 6.681%. Okay? So p-value is 6.6%, which is greater than the 5% significance level. So either case, the null hypothesis is not rejected. So null hypothesis is not rejected. And if you take the critical value approach, should be the result should be the same. Let me do it by myself. Like the critical value will be calculated this way. Mu is 80% your hypothesis, and Z alpha is 1.64, and you are going to use positive, like plus here, because it's upper tail test. So you are going to use plus. The critical value must be greater than your null hypothesis. Standard error, as usual, and you get this. So you are going to believe that the policy change has any effect only when the sample average is greater than 86.56%. But in your data, it's only 86%. So not sufficiently large. Your sample is not sufficiently large to prove that the policy is sufficiently effective statistically. So that's, again, how we make the decision based on the critical value. But we are going to use this critical value now to evaluate the error probabilities, type 1 and type 2 error probabilities. What is the type 1 error probability? Remember, the critical value is given here. It is your calculation. We are using the same numbers. Okay, the type 1 error probability does not need any algebra. It is always significance level. So automatically it is 5%, right? No need to calculate anything, right? So always. But type 2 error probability requires some computation. I will assume that actually the truth is 90%. After the policy change, actually the coverage rate was 90%, but just if you are unlucky, in your survey, you happen to have more uninsured people, then what is the type 2 error? And remember, in this case, because we are assuming that the truth is 90%, you have to use standard deviation according to this truth for standard, like when you standardize the probability. So 0.9, probability 0.9 implies a standard deviation of 0.3, right? So use this for your algebra. Okay, let me turn the page. This is the last page. So the standard deviation is 0.3. So we are calculating type 2 error probability. And type 2 error happens when you don't reject a wrong hypothesis. So when you don't reject, the sample average must be smaller than the critical value because it is an upper tail test, right? So if the sample average is not large enough, you cannot reject. And you are going to standardize this random variable using the truth that you are assuming. You assume that the actually uninsured rate increased to 90%, which implies mean 0.9, standard deviation 0.3. So you will get this number after standardization. And if you plug this into the standard normal calculator, you are going to get 12.507%, which is the type 2 error probability. This is the probability that you fail to reject the null hypothesis, even though the null hypothesis is wrong. On the other hand, then on the other side of this probability is 87.493%, which is the power, which is the probability that you can correctly detect the increased probability, right? So in this computation, like if the probability increases from 80% to 90%, you will be able to tell the change with 87%, but you will fail to tell the change by 12.5%. Okay. Okay. Yeah. Thanks. This is the end of chapter 10. In the next video, we will change our topic, like to correlation, covariance, and correlation coefficient, which will be a new topic. So it's also very interesting. Okay. Thank you for watching, and I'll see you there. Bye.